our body. So a buffer buffers the pH level of a solution. That means pH level does not change dramatically. Even after adding an acid or an or a base. Even after adding so a buffer can be a buffer in both directions, in the direction of acidity or alkalinity. And we even can create a buffer which buffers more in the direction of acidity, but not to alkali, or vice versa. And that's depending on the system. If we are expecting an influence that while the reaction is ongoing, it always gets more acidic, we try to have a buffer buffering these additional acidity, but we don't need it in the alkalinity, or vice versa. And if we don't know, is it going in the alkali or acidic range, we take the middle. The buffer capacity should be in both directions. And one familiar or famous buffer is the acetate buffer. And the buffer is always the salt of an acid and an acid, or the salt of an alkali and the alkali. Here it is the acid and its salt. So buffer is always here an acid and a salt, or an alkali and its salt. And this is special buffer buffers a pH level in the area of 5. Because this is the pKa of the acetic acid. It's 4.74. And in this range, it buffers the system. Yes? For example, for an aspect for a CCAA, and instead of the sodium, but then maybe let's say a magnesium aspect. So it's twice times 2. Would that buffer be more powerful, or like what? Well, it is always depending on the initial salt which is built. In this case, you have the magnesium hydroxide and the acetic acid. So you write 2 times the acetate ion with 1 magnesium, but the magnesium hydroxide is a weaker alkali compared to sodium hydroxide. So here it will be more in the direction of acids.
Any other question? So titration or neutralization is one topic. Now we come to a next subtopic. We are always now in the topic of chemical reactions. Subtopic 8 now is redox. We talked about acids and alkali, and now we talk about redox processes. Redox, what does the redox mean? Do you know? It's reduction and oxidation. Well, I think you know what's oxidation. It is a release of electrons, yeah, losing electrons. And what's reduction? It's the opposite, thank you. So electron uptake. So this is really now really pure chemistry. We talked about chemistries dealing with the transfer of electrons. So in general, we have a partial oxidation. We call it oxidation, ox, in future, and red is for the reduction. The ox is, for example, we have A, any molecule or element A, which is oxidized, and we have the oxidation number of A at the beginning is M. And we are losing or releasing Z electrons. What will be the oxidation number and the charge of A? M plus Z, and the charge will be Z plus, or plus Z as well. When we look, the oxidation number is increasing. Oxidation number increases. Of course, for the reduction, we have the opposite situation. We have an element B. Now we take up the number of Z electrons, and we end up at the element B as an anion with the number of Z negative charges. And the oxidation number here, we call it N. Now what's the oxidation number here? N minus Z. So here the oxidation number is decreases. So that's general oxidation reduction. Most of you know about it, but let's have a look to a few examples. For example, we look to iron, elementary iron. And there is an oxidation to iron 2+. If you look to the periodic table, you use the PubChem. I have it here. What is typical for iron in the field of the oxidation numbers? Iron is a transition metal. We have here on the other side all options in the field of oxidation numbers for iron. It could be quite a lot. It could be -2. It could be 0, of course. It could be +2, +3, and +6. The most which we will find in nature is +3. But when we look now to this equation, even +2 is possible. So this is an oxidation, of course. We have here, when we transfer it from 0 to +2, 2 electrons are released. The other one is iron can even create the iron 3+, then 3 electrons are released. It's an oxidation as well. The oxidation number +3, 0 here. So both possible. And these are the main reactions of corrosion. When we have some iron out, you see after a while what can be observed if you have a pure iron and put it out into the rust. And what's the color? Brown, red, orange. So it's a mixture of 2+, 3+. There are a lot of different oxides as well. Yeah? The first one is green, and then it's getting brown. And we even have some more black oxides of iron, these mixtures. So, well, let's look to the reduction. We have the Cl2, the chlorine gas. Now we add 2 electrons, 1 to each of it, and we end up at 2 chloride anions. That's a reduction. 0, -1. So 2 times we need 2 electrons. Oh, again, 1 chlor likes to take up 1 electron because then it ends up at the noble gas configuration, if you remember, the first things we discussed. For the oxygen, O2, what are you expecting? How many electrons oxygen will gain? 2, 1, 2. So the oxygen takes up 4 because we have 2 elements, 2 molecules. So 4 electrons and 2 O2 minus. It's a reduction. We can even have a look to these balance of iron 2+ to iron 3+. When we read it from the left to the right, what is it? We come from 2+ to 3+. It's an oxidation, so 1 electron is released. If we read it backwards, it's a reduction. So from the left to the right, it's an oxidation. from the right to the left, it's a reduction. So we have even here, the system could be a balance in both direction possible. It's just a question of energy. Is it more stable to stay at the iron 3+, or more stable to stay at the iron 2+? And that always is a question of the environment. If there is a partner, because a single electron never exists in chemistry. We don't have single electrons. If iron here is releasing an electron, there must be a partner who is taking that electron in the same moment. Otherwise, nothing happens. So it always is a question of the environment. Is there any partner who is willing to take that electron in this environment, at that condition? pH, temperature, other systems which are influencing, that are all having an impact on what happens. And to be sure what happens, we create a kind of table looking to each single reaction. When we look just to that, and then we can measure the power of oxidizing iron 2+ to iron 3+. And this is just a relative comparison to others. We compare that with another system. For example, when this is oxidized, for example, proton can take up that electron. And what is produced when a proton takes an electron? H+ takes up an electron. What is the product? Hydrogen gas. So first of all, we will observe the production of bubbles, of gas bubbles, hydrogen. And the second of all is we can compare if we have a solution of iron 2+ in a proton containing solution, when there is a production of hydrogen, then this power to form iron 3 is bigger compared to the power of staying as a proton for the hydrogen. So the hydrogen production is more. Here we have the reduction more effective, and here the oxidation. In this case, it doesn't work because that is not working. But in other cases, it might work. So we compare it. Why I'm taking the hydrogen example is because this hydrogen example is our standard. We say we look to these standard hydrogen electrode. The standard hydrogen electrode system is H+, or write it in the same way as we did it above. H2 can create 2H+ plus 2 electrons. And this is the standard. And we can compare this standard. We never know the absolute value of the power. We can't measure it. But what we can measure is we compare this with the iron system. And then we have a difference. And the difference we can measure. And when we do that with all the systems we know and formalize it and put them into a table, the table is called the table of redox potentials. You can look it up, the table of redox potentials. And if you're able to read that, you can decide, okay, this system will be oxidized and the other one reduced when I have those in comparison, those two systems. Because we always measure everything in comparison to the hydrogen system. And then we can make a row of redox potentials. And out of these differences, we can say, yes, this one will be oxidized, the other one reduced, or whatever. So in general, we have a reduced form and we have an oxidized form. Plus Z electrons. And these are in balance. The reduced form will be oxidized. The oxidized form can be reduced. When we read it from the right to the left, it's a reduction. When we read it from the left to the right, it's an oxidation. And this, again, as we had it in the acids and base, where we called it a corresponding acid-base pair, this is what we call a corresponding redox pair. As already mentioned, in chemistry, there is no free electron. No free electron occurs. So oxidation is always coupled to a reduction and vice versa. So now let's have a break, 15 minutes, and we will do some examples of reduction and oxidation and the overall redox reactions to get familiar with that after the break.
Following everything here, and so when you did chloride and it accepts the two electrons so it can hit the noble gas configuration. So I knew it's negatively charged, and the reason why it has -1 on the oxidation is that because of the
Yeah.
That's it. So it's something.
Yeah, and of course it took up an electron. So each of these atoms, one took one electron. Of two of them, so now they have one electron more than needed for the neutrality for no charge.
Yeah.
So it's negative charged. It must be in one time. And that is the oxidation number, just to have it clear from 0 to -1. That means one electron comes from for each of the atoms.
That's where that comes from.
That's just formal. N is now 0, and 0 minus 1 is -1. Okay, back again. Please sit down and be quiet. Now we're coming to some examples for redox reactions. A very simple one, the oxidation of sodium. Oh, we already mentioned, if you remember, coming back to the beginning, sodium is in the first column, in the first group. How do we call them? Alkali metals. What are you expecting for them? Are they releasing electrons or taking up electrons? Releasing, because then they give away an electron. In this case, it will end at the neon gas configuration when the 3s electron is released. So we will have an oxidation to the Na plus ion plus 1 electron. And when we look to another example, a reduction, we had it already, the chlorine gas. It will take up 2 electrons as mentioned, and we will end up at 2 Cl minus ions. Chlorine, the opposite situation is in the 17th group. How do we call this group? The halogens, and they take up an electron, and then it will end up at the electron configuration for the argon. Here we have 3s2, 3p5, and here 3s2, 3p6. 1 electron more as in the chlorine, but easily it will take it because then it's stable. And you see the -1 is the most common oxidation state for the chlorine gas. So here we have the reaction. This is a reduction. When we now formulate the overall redox reaction, we always said just before, never a single electron occurs. So when those two are reacting together, what do we have to balance? Yeah, here we have 2 electrons, here we have 1. What? Multiply by 2. So the overall reaction will be 2 sodium elementary. Then we have 2 electrons here, 2 electrons here. We can cancel. Plus chlorine gas forms NaCl, and this is 2 of them. Of course, it will be in solution. Maybe when we have it in water, it will be 2Na plus 2Cl minus. Depending on the surrounding, do we have the salt or do we have the dissolved ions? And this is what we call the overall redox reaction. Redox is oxidation and reduction. That's the redox reaction. Again, try to translate it into a general form. We have a redox pair 1, and we have a redox pair 2. Because at the end, we very often said, in theory, it can go in both directions. We can say it could be right, left to right or right to left. Even here, in theory, it could be right to left or left to right. So we are balancing, and we always say this is the reduced form, which is oxidized, and the oxidized form can be reduced. For the sodium, it won't work very easily because normally it's oxidized. If we want to push it to the left side, we have to add energy, electrons. For the chlorine, vice versa. Normally it will go in this direction, but we can even oxidize it via power from outside to push it in the opposite direction. So here, this is the oxidized form, which is reduced, and this is the reduced form, which can be oxidized. So here in the redox pair 1, we have the reduced form 1, which is oxidized to form the oxidized form 1 plus set number of electrons. And the oxidized form 2 will take up set electrons to produce the reduced form 2. And the overall redox reaction is red 1 plus OX2 forms OX1 plus red 2. Each of those partial reaction can be read as a reduction or an oxidation. For the example chlorine, Cl2, that is the oxidized form, which can be reduced to form the reduced form. That's the oxidized form. So ox, and that's the reduced form. We call that red. And the stronger the tendency of the oxidized form to be reduced, the weaker the tendency of the reduced form to be oxidized. It's clear, huh? and vice versa, the stronger tendency of this form to be reduced, the weaker the way back. Or the stronger tendency of the reduced form to be oxidized, the weaker the way back. When we are now looking to more complicated examples like we did it here, let's have a look to a more complicated example, creating redox equations. We look to copper, Cu, elementary. Is put into a solution of nitric acid. Do you know the formula of nitric acid? Oh, so HNO3, that could act as an acid. It is creating H plus ions plus NO3 minus. What is now important, HNO3 is not only an acid, now we mix it up with redox. HNO3 can act as an acid and is what we call it an oxidizing acid. So HNO3 is an oxidizing acid. And I will explain what it means. So it's an acid and it acts as oxidizing reactant. Oxidizing means itself is reduced, but it is oxidizing other partners. And that is how we call it. Oxidizing agent mean itself, it's reduced, but it's oxidizing another one. So now in our example, we have the copper. So what will be oxidized when we have copper elementary in HNO3? The copper. When we look it up in the periodic table, always that is the main tool. Where do we find the copper? In this 11th group here. Yeah, if we look it up, what is the most common oxidation number for copper? +2. Well, that's all in the periodic table. So now copper will be oxidized. So our redox pair 1 So the redox pair 1 is the reaction of the copper elementary, and it will be oxidized to form copper 2+. So how many electrons are released? +2 electrons. What is the oxidation number of the element copper? No, 0. In the elementary form, it's 0, and here it's +2. That is simple. Huh? But now we have to look to the nitrate, the redox pair 2. The NO3 minus. When copper is oxidized, so what are we expecting here? What will be reduced? Do you remember the rules of oxidation numbers? How to place oxidation numbers? What's the oxidation number of oxygen? -2. So it's always -2. What does it mean for the nitrogen? Oh. -2 times 3 is -6. So what is the oxidation number for the nitrogen? No. No. Guys, thank you. We have one negative charge remaining. So -6, 1 is remaining. It must be +5. So +5 is 1 for nitrogen. If we look it up again, periodic table. Yeah. Now, for the nitrogen, it's getting a little bit complicated. +5 possible. Yes, we have it. But now it can be not more than +5. Why? Well, let's ask, why is +5 the highest number for the nitrogen? Not the argon. Nitrogen, we can take away 5 electrons. 1, 2, 3, 4, 5 maximum. And then we end up at helium. Or we add 3 of them, 1, 2, 3, then we end up at neon. So the -3 is even the most common one. You see, -3, 1, 2, 3. This is what we find very often. For ammonia, for example, NH3, the proton has +1, so 3 times +1, and the nitrogen has -3. That's the most one. But here in the NO3 minus, we have the +5. We are at the other end of, we are at the other max position of the oxidized form. So the only way it could act is gaining electrons. It cannot more handing over to other partners because it already is in that max position at +5. So what can be done is it can be converted to a +4, +3, +2, or even -3. And that's the complicated example. It could happen quite a lot. We have a lot of different nitrous oxides which can be created. And we call them NOx because when we have NO, what is the oxidation number of nitrogen in NO? +2, possible. When we have NO2, +4. When we have N2O5, +5. So there are a lot of different nitrous oxides. That's why we call them in the mixture NOx, because it can be 1 to 1, it can be 1 to 2, it can be anything different. A lot. And do you know something about these NOx? They are hazardous to health. They are cancerogenic. And they are created in the combustion processes in all When we burn our fuel in our cars, what do we have? In the atmosphere, what is the main component in the atmosphere? Carbon monoxide in the atmosphere. Oh, hi. You won't live. In the atmosphere, what is the main component? Nitrogen. Please, these numbers are really relevant. 78%. You inhale it every day, thousands of times. 78% nitrogen. What's the next one? How many percent? 21. And the next? Noble gases, nearly 1. And then the next? CO2, not carbon monoxide. Carbon monoxide, you will die immediately. So hopefully there is not too much. So and do you know the current CO2 concentration in the atmosphere? It's a greenhouse gas, you know? No. Not methane, CO2. We are talking about CO2. 420 ppm. 420, which is 0.042%. You can volume percent. So 420 parts per million. Each year we increase 5 parts per million. That's the big problem we have. Currently, they are in Dubai talking about the IPCC's meeting there about the global change, the conference of the parties now, the 28th. Now they are talking about what happened in the last 5 years. In Paris, 5 years ago, they fixed to that 1.5 degrees Celsius goal worldwide, which should be the max of the increase of the average temperature. Now we are here in Germany at 1.7. Only Germany. Worldwide, something like 1 to 1.4. The max should be 1.5. And we do not think that we can achieve this goal currently. But coming back to the NOx, in the atmosphere, we have a lot of nitrogen, we have a lot of oxygen, and when we burn fuel, when we burn coal, when we burn oil, whatever, the temperature is something like 1,000 to 1,200 degrees Celsius. Normally, nitrogen and oxygen in the atmosphere, there is no reaction, no NOx are built. But at that high temperature, there is a creation of NOx. And we have it in the exhaust gas of our cars, of chimneys, of industrial processes. And this is not very healthy to us. For example, in Munich, when you are living nearby the internal ring street, we call it the Mittlere Ring, middle ring, where the cars are driving around Munich, you have the highest NOx concentration in Germany. So living there is not very healthy. And there are a lot of things to reduce NOx. Do you know how this is done in the car? Again? Yeah, with what? What do we add? Yeah, but for the NOx reduction, we have one special thing. AdBlue. Do you know what AdBlue is? Yeah, mostly for the diesel cars, but what is the principle behind, or what is AdBlue from the chemical point of view? No. A catalyst is not, you don't use it in the reaction. The AdBlue, you have to fill it blue from time to time into your tank. What is it? Yes, yeah, you're right. But what is it? Sorry? I don't understand. So when you have the NOx, it's the oxidized form of the nitrogen. What could be an idea to add? The reduced form of nitrogen. So ammonia. If you add in the AdBlue, there is ammonia, NH3. Here we have the N in the -3 oxidation number, and you mix it with something NOx where N is a +2, +4, +5. And they are reacting together to form nitrogen, because the reduced form handles over electrons to the oxidized form, and in the middle, nitrogen is created. That's the trick. Here, we are not sure what happens. So I always will give you an example if you have to create the redox pair 2. And let's say we end up at NO. For example, what is the oxidation number in NO? We already said +2. So how many electrons are needed in the reduction? 3. So we have +3 electrons. We now look to this equation. Please concentrate. This is the most complicated thing for most of you when you have to do that in the exam. First, now have a look on it. Okay, 3 electrons are transferred. It's a reduction. Okay, but now the balance is not fine. We have 2 problems. Here we have 3O, we have only 1 here. And the second problem, we have 4 negative charges on the left and no here. So here in between, of course, we have the arrows. So we have to balance the second pair, and therefore we are in an acidic environment because we added HNO3, which is an acid as well. It's not only oxidizing, it's even an acid. So what could be the idea to balance the charges in an acidic environment? First of all, add the H+ ions. How many do we need to add? 3. Then we have 3 negative plus 3 positive, but 1 negative remaining. 4 plus 4H plus. And now we check the element numbers. We have 3O. N is already clear, but only 1 O here. We have 4H and 2 O remaining on the left. So how many water molecules are produced? 2. Yeah. So now this is done, but when we now try to create the overall redox, again, check the number of electrons. Here we have 3, here we have 2. It must be a transfer of the same number. So how can we do that? Loud? Multiplying by 3 and multiplying by 2. Then we have 3 kappa elementary, nothing left on the first row, but then 2 plus 2 nitrate ions. Then we have 6 electrons here and 6 here, so we can cancel, but plus 2 times 4H plus is 8H plus. And we create 3 kappa 2 plus ions plus 2NO plus 4 water. That is the overall redox reaction. So, well, for the second redox pair, we have to balance the charges and we have to balance the number of elements. So the number of each element must be the same on the left and on the right side. We are not able to create elements or to destroy. And now what is important, in an acidic environment, we balance the charges with protons. What will we take in an alkaline? OH minus. So this, please keep in mind, in an acidic environment, we take H plus for balancing. The number of charges or the charges. And in an alkaline environment, we take OH minus for balancing the charges. Let's do another example. Redox pair 1 again is the same. Well, we have the copper forming the copper 2 plus 2 electrons. But now the redox pair 2, we have the NO3 minus again, but now not NO, we say NO2 is formed. Please help me now in creating the overall redox reaction for this example. First of all, what do we have to do? First of all, balancing the charges. Huh? So here we have +5 again. So what's the oxidation number here? +4. So how many electrons are taken? 1 plus an electron. So now in an acidic environment, balancing the charges, what do we have to do? How many? 2. We have 2 negative, so we need 2 H plus. And now what is created on the right? What? No. Water. If we create hydrogen gas, there's another redox, because then here the hydrogen will take the electron, but that doesn't happen in this case. So let's check 1N, 1N, 3O, 2, 3O, 2H, 2H. That's fine. Now the overall redox reaction, how does it look like? Second by 2. Then we have the copper plus 2NO3 minus 2 plus 4H plus. And we have here 2NO2 plus 2 water. Fine with that? Oh, we check. Of course, plus kappa 2 plus. I forgot. Thank you. So it looks slightly different to the above example when we have NO2, but both possible. It can be NO, it can be NO2, it can be even another NOx. And that we can see. We will have an example in the lab session. If you grade or pass the exam, you can join in the lab session next semester. And there is an example. We have to do these experiments under the fume hood because these NOx are really cancerogenic. To be sure that you do not inhale them, you have to be really careful. Do it under the fume hood. Here, it's sure that all the gas is sucked out into the chimney. And you can see it. The mixture of different NOx gases have a brown color. So they are brownish. The fume of brown gas, always be careful. It could be NOx. Okay. Now we come over to discuss about the principles of a battery. Because the battery, at the end, it's a redox reaction. But to understand, we start with a simple example, which we call the galvanic cell. The galvanic cell. Well, let's draw a figure. We have a beaker. This is our beaker. And in the beaker, we have an aqueous solution of copper 2 plus ions. For example, we can create that solution via solving copper sulfate. Copper sulfate, what is the oxidation number of oxygen in the copper sulfate? -2. -2. What is the typical oxidation number of copper in the oxidized form? +2. What must be the oxidation number of sulfur? +6. So we have the sulfate ion SO4 2 minus, and we have the copper 2 plus ions. This is the copper sulfate in water, always solved, so aqueous. Aqueous. And we are now only focusing on the copper ions because this is what we are interested in. We don't care about the sulfate. Now I'm integrating an elementary zinc electrode. This is a solid elementary zinc. What's the oxidation number of elementary zinc? 0. So here that's 0. Here that is +2, of course. Now, what are you expecting when I have a setup like this? Reaction, yes, but what? What happens? Again? What? Zinc will be oxidized, and what happens to the copper? It will be reduced. When we look to zinc, let's have a look to zinc. Can you find it? What is typical oxidation number? 2, +2. Same as in copper. The main is +2. It could be +1. Here we have the +2. So there will be a reaction of zinc. The elementary zinc will be oxidized, and it will form Zn2+, plus 2 electrons. And because we know never single electrons, in the same situation, the copper 2+ will be reduced. It takes 2 electrons to form elementary copper. So what can we observe after a while when we're doing this experiment? Yeah. Yeah, or on the surface of the zinc. So there will be a coating of copper step by step and cover the zinc. So we will have a deposition of copper elementary on the surface of zinc. When it's totally covered, then the reaction stops, because then it's copper and copper 2+, so there is no way. If this is totally covered. So metallic copper deposits on the zinc rod. And zinc dissolves. To form zinc 2+ ions. That is what happens. And this is the case because copper is a noble metal and zinc not. So copper stays quite stable. If you have copper outside in nature, it won't be oxidized very easily because it's very stable. It's a noble metal. Do you know metals even more noble than copper? Silver and gold, platinum. Of course, they are even more noble. Platinum, for example, you use that when you have some broken legs, whatever, integrated to put together your bones again. The doctor takes platinum nails or platinum screws. They are very noble. Zinc not. So in this case, you even can think about your normal knowledge, which of the metals will be oxidized and what will be reduced. Iron, for example, is not very noble. It is oxidized. It is, we call that corrosion or rusting. Rust is built. Copper, it's stable. So if you have an application outside you should think about using iron or copper. We don't use iron normally very often as pure iron. We are creating steel, and I think we already talked about adding carbon to iron. Then we have a mixture of carbon and iron, and that is what we call steel. And steel, there are different grades of steel, different qualities, is more stable against corrosion compared to iron. So this is the way as it acts without any additional energy input from outside. We just put together zinc and copper ions, and electrons are transferred. This is how it works by itself. When we are now able to create a system where we can use the electrons in another way, we can even have a creation of work, because the electrons are moving from the zinc to the copper, and maybe we can light a lamp with that, because that is the flow of electrons, which is electricity. But in this case, it doesn't work because there is no wiring. It's a direct transfer. So we think about a new setup of the same system where we can maybe use that flow of electrons. And this is called the Daniell element. Daniell element. Mr. Daniell was the inventor, or he found it first. We separate those two systems in two different beakers. We have one beaker on the left side. And we have one beaker on the right side. On the left side, we have just the system zinc and zinc 2+. So here we add the zinc sulfate. So we have Zn2+ ions solved in there. And we have a zinc rod, elementary zinc, in there. Now we call it zinc electrode. This one is what we call zinc electrode. It's elementary zinc. On the right side, we have the same now with copper. Here we have the copper sulfate and a pure copper electrode. And the copper 2+ ions in there, we created adding copper sulfate. Always in an aqueous solution. Now we add something additionally, we call it a salt bridge. This is our salt bridge. This is needed to create a circle for the flow of charges. And we have here an electrical wiring of the zinc electrode. And we can measure even the power, the voltage of this when electrons are moving towards the copper electrode. Now we have here electrons are flowing, moving from the zinc because the electrode is oxidized to form more zinc 2+. Electrons move and they are used to create more elementary copper via reducing copper 2+. And the exchange of charges via the salt bridge is the movement of the sulfate. Because in both cases we have sulfate. We can measure the voltage here. And in this example, the voltage difference E is 1.1 volt, which we can measure. On the left side, zinc is dissolved, the zinc rod dissolves. So zinc is oxidized, zinc 2+ is built, 2 electrons are created. On the right side, elementary copper is deposited. So the copper 2+ is reduced and it forms copper elementary. So here we create a bigger copper rod, and here zinc is dissolved to form zinc 2+ additionally. And this is copper 2+, which is created more and more. So the zinc rod gets less heavy. The copper rod gets thicker and thicker and more heavy because more copper is created. What we measure is the delta of these potentials, the delta E. We cannot measure the absolute value, plus we measure just the difference. So delta E is 1.1 volt. And due to the difference in the redox potentials between the 2 electrons, we have these, well, difference. That is due to the difference. It's created due to the difference of the redox potentials of the 2 systems. The overall reaction is we have elementary zinc and we have copper 2+, and what is created is zinc 2+ and elementary copper. That's the overall redox. And this could happen because the place of the zinc system in the table of redox potentials is above the copper system. Now we will see it. The place of the zinc system is above the place of the copper system in the table of redox potentials. In this case, it's a plus. The reaction, or what is the question? Here it is in this way, the delta is plus 1.1. I don't understand the question. Copper minus zinc. Mhm.
Should be something like the potential of zinc minus
Yeah.
in the case like this, value is because of the value of zinc.
Uh-huh.
Zinc minus
Yeah, yeah. Copper minus zinc, I think. Let's look to the table. We will see it. Huh? Zinc. What sure is zinc is less noble as compared to copper. Let's draw that the electrochemical series, and then we can see. So the electrochemical series or the table of redox potential. Series, I think it's written like that. Series. So it is a very formalized way how to write it. We already know we have a reduced form. And we have the oxidized form. And we have that standard redox potential in volt. E0 means that's the standard redox potential. Now we create a table. And the standard redox potential always is measured in comparison to the hydrogen system, as mentioned before. Let's start with lithium. The reduced form Li, what will happen to lithium? It is an alkali element in the first group, so it will be oxidized normally by itself. The oxidized form is the Le plus, and we have one electron created. So the oxidation is from the left to the right, and the reduction possible from the right to the left, but it won't work by itself. If we want to reduce lithium ions, we need energy. So from the left to the right, we have a negative potential. Negative means it works by itself. And the value is minus 3.04 volt in this example. Potassium is the next. Potassium, even an alkali element. So what are you expecting? Will it be oxidized or reduced? Oxidized as well. So here, potassium, first group as well, K plus 1 electron, but the power here is a little less, only minus 2.92. The next one is zinc. We already talked about, not very noble. So it normally is oxidized quite easily, but now we have zinc 2 plus 2 electrons. That's the reaction, because zinc plus is not built. And here the value is minus 0.76. So here we see it is not noble, but yeah, it is oxidized. Little more noble is the iron. When we compare it here to form the iron 2 plus 2 electrons, this is minus 0.41. We do not write all the systems. We can look it up in different tables online, just a few. And then at any time we come to the hydrogen system. When the hydrogen is oxidized, it forms H plus, 2 of them, plus 2 electrons. And we say by normalization, this standard, that's the standard system, and the redox potential is 0. We just say that is 0. When we compare everything with the hydrogen system, so this is our reference. That's the reference. And we call it the reference standard hydrogen electron. The reference standard hydrogen electrode. In reality, it's not pure hydrogen. It's water, and we have a platinum electrode. And this is because hydrogen is not a metal. We cannot have an electrode out of hydrogen gas. So we take a platinum, which is very noble electrode, and have hydrogen as a protons and hydrogen gas, which can be oxidized or reduced. That's the standard. And we cannot measure that as a single. We do not have an absolute value. We just compare it. Coming to more noble metals, now we come to the copper, for example. We know when we oxidize it, copper 2 plus is built and 2 electrons. But now that needs some power from any other system, because normally it is not oxidized. So we have a positive redox potential, 0.34. Going to silver, we see silver plus only 1 positive charge plus 1 electron. Here we already have plus 0.8 is the redox potential for silver. And when we go on now, moving away from metals, coming to halogens, the reduced form of chlorine is the chloride. 2. And then when we oxidize it, chlorine gas is built, plus 2 electrons. Here we have a redox potential plus 1.06. And the most stable one is the fluorine, F minus. Even here, fluorine gas and 2 electrons. Here we have plus 2.87. And this is a small view into the table of redox potentials. Of course, there are many more systems, but to show you that's the strategy. So the tendency to be oxidized is increasing bottom up here. So tendency to be oxidized increases bottom up. And the tendency to be reduced increases top down. Yeah, so as we go down, the stronger the oxidizing agent, which is reduced. So here it will be way from right to left side by itself. And here it will be the way from the left to the right side by itself. Yeah, if you now look to that, we had the zinc system compared with the copper system. So we have here those two. We have to compare. When we compare them, what is the delta? Yeah, now look just to the value. We have here negative minus 0.76, and here we have positive plus 0.034. What is the delta? Yes, the delta here is 1.10 volt, and this is exactly what we measured. We always have to focus on the delta. Here we are in the negative side, in the positive side, so the delta is minus 1, is 1.1. And we just look to the delta. Here, what we call, how we call them, these are alkali, and all of them, we call them the base metals. And those here, we call them the noble metals. Of course, not the chlorine, fluorine, because this is not a metal. Here we have looking to halogens. Well, when we look to our system, we have the system we already discussed. We have the iron, or another one not discussed in detail, iron, and we compare it with copper. Let's look to it. Iron can be oxidized to form iron 2 plus 2 electrons, and copper can be oxidized to form copper 2 plus 2 electrons. So now what are you expecting? When we look to the redox potential of iron, it is minus 0.41 volt. And the redox potential of copper is plus 0.34 volt. Now, what are you expecting will happen? Will iron be oxidized, or will copper be oxidized more easily when we have a mixture of iron and iron 2 plus copper and copper 2 plus? What will happen? Copper will be reduced. So the overall reaction will be, because this goes by itself from left to right, and these needs energy, but it comes from the oxidation of the iron. So we will have iron and copper 2 plus will form iron 2 plus copper. And what's the potential of the overall redox reaction? Yeah, the delta E is 0.75 volt. And that is exactly what we can measure in a setup as we had it in the Daniel element. Is that clear? This is important. So please keep in mind, a negative value means not noble. It is more easily oxidized. A positive value means more noble, or it will be more reduced. And what we can measure is only the difference, or we normalize everything comparing with the hydrogen system. Everything is measured with the hydrogen system. And when we measure this, we can even see, okay, it's true, because the delta, it can be measured directly, or we measure this system comparing with the hydrogen and measuring this system comparing with the hydrogen, and then calculating the delta. That's, of course, the same as we can measure. So it's working. The system is, fine. So you can look up these redox potentials in any tables, and then you can figure out what might happen when we have a system mixed with two different systems. And we can compare. Is it more an oxidation of A or B? So base metals are located above the standard hydrogen system, and the